Number one, I know T2 is bigger than T1. Number two, the tension in all the other places is actually still less than T2. Why do I call it position 2? Oh, sorry. This should be position 2. Okay. Should I call this 3 and 4? Anything lah. I just put 1 and 2 here. So here is enough already to answer most A-level question. But I will bring you one step further. Okay. And I'm going to talk about position. What am I going to call this? A and B lah. Okay. So, or maybe instead of talking about A and B, I talk about an intermediate place. The in-between. The Middle Earth. Here. At an angle like this. Yeah, miss angle like that, then how? Don't worry. You can resolve vectors, right? I'm going to zoom in a bit and show you what's going to happen now. So let's say this is T lah, any arbitrary T. We definitely know that there is tension and there is mg pointing downward. These two, no problem. Then some of you may be thinking, oh, miss, conical pendulum, horizontal circle. Well, I would say yes, but no. It does look a lot like the horizontal circle, but actually it's not, because again the circular part is vertical. So when we resolve T, we have to be very mindful. Where is the direction of acceleration? Where is the direction of net force? It has to be directed to the center. Directed to the center of the circle. Like that. So how, teacher? Well, you got to resolve somebody. Well, we don't have to resolve tension, because tension is always, tension is always in the same direction as your centripetal force or your net force or your centripetal acceleration. Look at this tension, because it's rotating in a vertical circle. So in this case, you can leave tension the way it is. What you have to resolve is actually mg. Oh, okay. So we're going to resolve mg now. Let me pick out a different color. I'm going to resolve mg, one in this direction and one in this direction. And the reason for resolving like this is so that whatever this component is, it will cancel off with t. So this one is our theta. So if you split mg into 2, this will be mg cos theta. Okay, so again, I'm going to think about the direction of force, the force in this direction. Okay, so the direction of net force is pointed towards the center of the circle. And the forces that is in line with this direction will be T and mg cos theta. So based on this, right, what I can write is actually, on the right here, net force is equal to T, because I'm taking the direction of net force as positive. So basically, I'm repeating what I did here, just at an angle, right? So if I take this direction as positive, this is positive. It looks like X. So do I write positive like that? Okay, never mind. Take that direction as positive, so that is your net force. Net force will be T minus mg cos theta. Okay, because mg cos theta is opposite the direction. So any kind of force in this direction will be negative. So you are negative, you are positive. You can? Just like if I look at this force, if this one causes you a little bit of confusion, it's okay, take your time. Choose a direction to be positive. mg, same direction, positive. T1, same direction, positive. Because you want the net force to be positive. Okay? In this case, again, same direction, same direction, same direction. Positive, positive, positive. Sorry, this is negative, my bad. Because this is opposite direction. So mg is negative. So use the sign convention to guide you. Okay? Down here is negative. So yeah, so I'm going to do it again here. The only difference is towards the center of the circle is positive. So T is positive. away from the center of circle is negative, so mg cos theta is negative. You may be thinking, what about the mg sine theta? The mg sine theta here, that's why the tension is not as straightforward as this one, but I simplify it, okay? So there's actually another tension component to balance this. So to make life easier, I'm just going to stick with this for now, okay? So what I actually just want to show is that when is your tension maximum, sorry. So I rearrange this, I will get tension as equal to net force plus mg cos theta. Or in other words, net force is centripetal force, Fc plus mg cos theta, and tension will be mv square over r plus mg cos theta. My friend, when is this value maximum? T is maximum if let's say you know a bit of trigo, when cos theta is equal to 1, because theta is all values between -1 to +1. So when cos theta equal to 1, this means theta is equal to 0 degree. When theta is 0, you look back at this diagram, it means that we are at position 2. So theta 0, this is immediately related to position 2. Okay? So T2 is equal to maximum. And what is maximum T2? T2 will be mv square over r plus mg times 1. Okay? mv square over r plus mg. As previously derived here. Oops. See here? mv square over r plus mg, mv square over r plus mg. Okay. Let's try minimum. Okay. So T is minimum when cos theta is -1. Not 0, my friends, but -1. So when cos theta is -1, your theta will be equal to -1, 180 degree. Where is 180? Position 1. Okay, you circle up all the way, half a turn, 180 is at position 1. So I can put that in. This, my friend, is position 1. So T1 is minimum, and T1 is equal to mv square over r plus mg times -1. So mv square over r minus mg. This is your T1. So I have proven using equation, okay, that T2 is bigger than T1. So when this one is 0, I'm talking about here. This is position 2. And when this one is -1 or theta is 180, this is position 1. So we measure theta from here to here. This is 180. Okay, can? So it depends on where your object is lah. In this case, my object is up here. Oops. In this case, my object is up here. In this case, my object is down here. Okay, so if you might be thinking, well, actually I play yo-yo and I know this. Great. But now is the time to actually calculate it lah. So you will be able to see that if let's say I want the spring to break or any breaking will happen, it has to be when T2 is maximum. Okay, so T2 is maximum. Okay, let me put a different color. Here is where the string may break. Because the string cannot withstand infinite tension. Maybe you reach a certain point where the tension is just too much, then the spring will break. Oh. Do you know why the string here have to work so hard? Because it needs to do two things. Number one, this string needs to support the weight mg. Number two, this string still need to provide centripetal force. Wow, so tired leh, so letih. You have to carry the weight of the yo-yo or the object, and you still need to provide centripetal force. Phew, life is tough. That's why the string may break, because it's doing two things at the same time. Now, when the tension is minimum on top, what is the difference? Well, when the tension is minimum on top, right, sometimes you may be moving too slow. The reason why the tension here is minimum is because the mg helps T1 to provide centripetal force. Okay, so what I mean by that is, if I go back to this equation, you see this one here, mg and T1, they work hand in hand, bekerja sama, work together, 分工合作, they work together to provide net force together. mg plus T1 is net force. So because of this, right, the T1 is actually pretty chill. He's like, bro, my friend gravity is helping me out here. So I don't need to support the weight. Not only I don't need to support the weight, I don't even need to provide centripetal force. Or rather, I only need to assist mg provide centripetal force. So mg and T1 in the same direction, T1 is smaller. mg and T2 in the opposite direction, T2 is bigger, because T2 needs to do double work. Support mg, provide net centripetal force. This one work together with mg to provide centripetal force. Two person do one job. This is one person do two jobs. One force do two things. Two force do one thing. You tell me lah, which one got larger tension? So obviously it's the minimum. But there's a danger about going too slow. So if you've ever tried to do the loop thing, okay, you will notice that if you are too slow, the yo-yo actually cannot complete the circle. Or let's say you go playground lah, and if you want to, I do not suggest you do this because it's vandalism, but let's say you push the swing, and the swing can go like that and come down. You have to push it fast enough, right? So when you are too slow, by the time you reach here, you don't have enough tension in the string to carry over, because tension can never be negative, and when it's zero, the string will become slack. Okay? So this minimum here, this is where the string becomes slack. So I'm going to write it down here. Something will happen now. So this T1 minimum, at this point here, the string can become slack, meaning T1 equal to 0. And when the string becomes slack and T1 equal to 0, you are unable to complete the circular motion. So if we cannot complete circular motion, it means that there is a minimum speed. Okay, so I'm going to now take this equation and try to find an expression for minimum speed. Okay, I'm going to write it here. Okay, so let's label a bit. At first, I look for position 1, and then I look for position 2. I found that the tensions are of different magnitude, so I decided to see if I could find tension in terms of theta, trying to confirm my understanding that the maximum is at the lowest position, which I have confirmed. So this is number 4. And tension is minimum at the highest position, which I have confirmed. This is number 5. Okay, so what is important for you to know is the limiting factors. The first limiting factors I talk about is if the string is going to break, it will break at the lowest position. The reason why tension is the strongest here is because tension does two jobs. One force do two jobs. This force have to be big. The reason why this tension is minimum here is because two force do one job, so the tension is small. It's very nice. Okay, so here, 6th and final point, we are trying to find the minimum speed of the object to sustain circular motion. Okay, so it's that minimum speed. So let me draw the top part of the circular part. So let's say this is the circle. Okay, and when your object is at this position, ding 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 ding, your yo-yo is here, this is the string. Okay, you obviously have our good friend mg, and you also have your t1. And where is the center of the circle? Center of the circle is obviously here. This is your c, so the direction of net force is here. All right, so net force here will be equal to mg plus t1. Okay, so at the minimum speed, the string becomes slack, meaning it loses its tension. So T1 is 0. So in this case, net force is only equal to mg. So I have mv squared over r, because net force is, as usual, centripetal force. Let me draw this one here. So write this another sentence for you. Another line, centripetal force is equal to mg. So from here, mv squared over r is equal to mg. So obviously, we can chop off the m, and we will get v is equal to square root of rg. There are a few interesting things here to note. Number one, the minimum speed is not dependent on the mass of the object. So you can be doing this with a yo-yo, with a 2 kg bowling ball, with your friend, and you vertical circle your friend on the playing ground swing. The minimum speed is only dependent on the radius of the circular part. So if the radius is small, then the minimum speed is small. If the radius is big, then the minimum speed is big. So I also, again, don't recommend you memorize this, but start from here. So this minimum speed of the object to sustain circular motion, we will take the top position. And the reason why we take the top position is because this is the smallest tension. So if any one is going to be 0 first, the string becomes slack, T1 is equal to 0. The smallest T will fall first. So smallest T, okay, let me write this in pen. Smallest magnitude of T becomes 0 first. Okay, so if the smallest T becomes 0 first, then the smallest T is T1 at position 1, at the highest position. Okay, so the two limiting factors is if you spin too fast, the string may break. That will be at the lowest position. Position 2, here. You spin too fast, the spring may break at this position. You spin too slow, there may not be enough speed for the particle to go up or the object to move to the highest position. So the string will become slack. This is the smallest speed. Drop below this speed, the weight or gravity will pull your object down. Okay, so that is what you need to know when it comes to vertical circle. Okay, what is important in vertical circle? Number one, tension is not the same. Okay, the whole point here is tension is not the same. Number two, you have to consider the tension point by point. Most of the time in your syllabus, we only care about the highest position where tension is the smallest and the lowest position where tension is the greatest. Maybe you can go and take a rope and tie around something to swing to feel the tension. Okay, so when the tension down here is the highest, this is where the spring will break. String. So I write here breaking point is here, lowest position. Okay, if let's say the object begin to slow down, here is minimum speed, you put tension at 0 at this highest position. So because of this, the only thing that provides centripetal force is weight. And then you can solve this equation. Okay, so that's it in a nutshell. If you want to know the variation according to theta, this part is me showing that indeed it is maximum on top and minimum down here. And I can actually think about all the tension in between. No? The tension would be maximum at the lowest position here, and then decrease, 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 minimum, increase, 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 maximum. Okay, so it will, here is maximum, decrease to minimum, increase to maximum, which is like the example I have shown you here, right? So if I play this again, you will see, okay, let me make this big. If I play this again, you will see that the tension is the smallest up here, and then it will increase and become the biggest up here. Okay, so let me try again. Tension is the smallest here, you see, 1320, and then the greatest at the lowest position. So you do see the tension decreasing, decreasing, decreasing to minimum, increasing, increasing, increasing to maximum down here. All right. You may be thinking, can I change the speed? You say there's a minimum speed, right? Can. You see, when I slow down the speed, the tension is becoming smaller. So I reach a point where if let's say I bring the speed down to the lowest position, let's see if it can go up. It can. There's still some tension. So this diagram doesn't show it, but if you actually do some washing machine front loading one, you will notice your clothing will go up, fall down, go up, fall down, because the washing machine is also a vertical circle. But how does the forces inside a vertical circle work, especially if, let's say, your forces, let me show you again. In this case, what provides the centripetal force is the interplay between mg and tension. But what happens when there's no tension? What happens when, let's say, I look in a washing machine, I put clothing in my washing machine, and the clothing will go up and fall down and go up and fall down. The thing needs to spin fast enough for the clothing to move in a circle. That will be in the next video, okay? So in this video, very important, you know that the direction of the center of the circle is the direction of your centripetal acceleration. Use that sign convention to help you write your resultant force equation, whether it's mg plus T1 is equal to net force, or T2 minus mg is equal to net force. 1 and 2 is what you need to know how to do. 3 is extra, to prove to you that T2 is greater than T1. Or maybe I should write this one like this. Give me a sec. My one not hang. Close. I will say T at the bottom is greater than T at the top. Okay? So number 2, for mean speed, T at the top is equal to 0. Number 3, for maximum speed before braking, T at the bottom is the maximum stress, maximum force lah. Means how do I know the maximum force? They must tell you in the paper. Okay, so you read the question, they will normally tell you in the paper what that maximum force is. So these are the 3 things that you should think of or be aware of, besides being able to draw the resultant forces. Okay, and I've proved all of it for you in this pretty long video about vertical circle. In the next one, we will consider other examples like washing machine and water in a bucket. And I'll see you in those videos. Bye-bye.